the BAe Hawk T1, a single-engined jet aircraft which entered service in 1976 with the Royal Air Force. Around 176 aircraft have been ordered by the Royal Air Force. Later on, many of them were converted to different versions for different purposes, and also some were sold to different countries. Because of being a two-seated aircraft, it was very popular for training pilots over many decades. Even today, the Hawk is used with the display team of the Royal Air Force, the Red Arrows. That video is dedicated to a part of the avionics of the Hawk aircraft, namely the attitude and heading reference system, as it was delivered with the first version of this aircraft. The manufacturer was Louis Newmark, which later on got absorbed into Smith Industries. For flying an aircraft, the most important instruments are the attitude indicator and the compass. These instruments give the orientation of the aircraft in three-dimensional space. They have to be reliable and very accurate over time. Exactly these instruments are controlled by the attitude and heading reference system in the BAe Hawk T1. So let's dive into that system by looking at the components presented on a workbench. That's the attitude and heading reference system of the BAe Hawk aircraft in the version as it was delivered, and that likely was replaced in 2011 to 2016 by a more modern system. So that's based on mechanical gyroscopes, a box with amplifiers and computation. That's done with transistors, op amps, and also some mechanics inside. So there's a gearbox inside for all the heading calculations. I'm very lucky I have the original test set which was used to debug the system in the aircraft. So via some breakout cables all the components can be connected to this test set. And here we see a very precise heading indicator together with the original attitude indicator from the Hawk, and a horizontal situation indicator which is borrowed from Tornado because it needs a servo, and that was what I had in my stock. So the system runs on 115 volts, 400 hertz alternating current. If we plug in this inverter that's creating this, we need around 50 watts of power to run the system later on. And you can already hear those instruments which are operated from the same voltage, and the supply voltage is also the reference for the synchro inputs. If I'm going to power up the system, in the first 12 seconds it will level the gyroscopes inside the box. And you will see red lights coming on here, which indicate that process, that the gyroscopes are moved quickly, and simultaneously the instruments are moving to the zero positions. And in the next 30 seconds the gyroscopes are spinning up, and after around 90 seconds the valid light should come on, which indicates that the attitude indication is valid and that the heading has adjusted itself to the value which is given by the magnetic input. And the magnetic input is also simulated here by this fraction of the test set. So here we can set an heading which is simulated as magnetic input for the flux gate sensor, which we now set around about to south. So now we will power up the system, and the first step will be alignment, with the first 10 seconds trying to do the course alignment, and later on the gyroscope spinning up. Let's start the system.
Yeah,
so
cool.
Now we see that small motor running. You see that something here is happening.
It's a bearing.
Yep. So now the gyroscopes are spinning up. The unit is trying to align the gyroscopes to their position. So the idea of that unit is that there are two gyroscopes inside. One gyroscope is determining the attitude of the unit, and one is for heading. You can see how the gyroscopes are slowly moved to the upright position as the attitude indicator comes to its nominal zero position. And as the gyroscopes are spinning up, that process is getting slower and slower because there's more force needed to torque the gyroscopes. But as soon as you are at the neutral zero position, the valid lamp, the yellow one, should come up on the system. So now you see the torquing light has switched off and now the welded light comes on. And that means from now on the attitude indicator is working properly, and we can see that if we are taking the gyroscope and we are starting to move the gyroscope, then we can climb or we can dive, we can rotate, and also the heading is updated. And if you hear closely, then you will hear also mechanical sounds from the control box. So there's inside some gears and some synchros which are doing a lot of the calculation related to heading, because that's quite complex calculation that cannot be done with op amps and transistors alone. For the following, I want shortly to explain an aerobatic maneuver called the Immelmann. It was invented by Max Immelmann in the First World War to quickly change direction of flight. In that maneuver, the pilot pulls the aircraft through vertical flight into inverted flight, and after that the aircraft is banked back to normal, upright and level flight. What happens if the aircraft is doing an Immelmann maneuver, which is flying overhead and then rotating, because then the attitude indicator would show the rear side of the ball. Let's try what happens in this system. I'm not taking the gyroscope and now I'm doing aerobatics, moving the aircraft vertically. I'm just doing the maneuver of rotating back again, and it's still working. So if that would be a very simple attitude indicator, this would stop working because it would be toppling. It would need pilot interaction, but with that system that can handle this. Now we're climbing again. Now we get the gimbal-flip, and then we are just rotating back. So that's very nice. So that means that's a really fully aerobatic system, and therefore it's used on the red arrows. Now let's have a look what happens inside the gyroscopic assembly by doing the aerobatics as before. Close. So now we have both gyroscopes in the perfect orientation, everything upright, and now we are trying to move the aircraft, and we can see both gyroscope assemblies moving in parallel. The roll axis is moving. Now we are doing the game of climbing. And in climbing we get the gimbal flip, and then we are rotating the aircraft again, and we are in the perfect upright position. We are diving. The gyroscope will do the gimbal flip again here as well. And back. Roll again. And everything is shown on the indicator as well. Other systems use one more complex platform with both gyroscopes on one platform, but in that approach with two different gyroscopes, the assembly gets more simple and everything is moving synchronously. Now we can see the heading gyroscope, which is maintaining its direction. It is flipping again. So flipping back. And now we are going back to ground. Thanks to all who contributed to bring that system back to life. Also thanks to those who helped in creating that video and who supplied material for the video. Last but not least, thanks to all of you for watching that video. Bye bye.